Alright, so crap, one more thing. I'm gonna go ahead and share the screen. We got everybody, right? Yep. Alright, so last class we did the um, first PowerPoint on gas equipment. This is the second one. Goes over AFUE and a little bit about combustion analyzers and things like that. Alright, when we've completed this section, we should be able to identify infrared gas heaters and how they operate, identify various types of infrared gas heaters, describe the operating characteristics of infrared gas heaters, and explain how to conduct a combustion analysis on a gas furnace, identify combustion analysis equipment and combustion byproducts that are important to the analysis, and describe the combustion analysis process and how to interpret basic results. Related performance tasks: complete a combustion analysis on a gas furnace or boiler. We probably won't get a chance to do that. I don't keep combustion analyzers personally. I think I know a guy that does. Maybe we can give it a shot. I don't do it that often. Combustion analyzers are extremely important if you're working on oil. I find that on most other equipment, as long as you got gas pressure set right and all that stuff, it's very rare that you really need to do a combustion analysis, but that's just my 2 cents. I mean, if you are doing combustion analysis, that's always much better than not. Combustion analyzers can also help you determine problems like possible cracked heat exchangers and things like that, but it's just not something I've done a ton in my career. It hasn't been up on the scale of things I thought were extremely important. So again, just my 2 cents, not necessarily something to live by. So infrared heaters, low intensity units like these generally require venting assistance from an induced draft blower due to the resistance of the long tube. This is one of the more common types I tend to see, is these long style infrared heaters with an induced draft blower on the end. High intensity units are non-vented. They become very hot and provide heat to a more focused area. Here's a couple wiring diagrams for them. They're generally set up a lot like a spark ignition furnace, so intermittent spark ignition. Basically, it's all your troubleshooting is going to be almost exactly the same. I don't even know if you can do hot surface ignition on them. I've never seen it done on any units that I've worked on, but when it comes to infrared heaters, troubleshooting it is, like I said, almost exactly the same as troubleshooting intermittent spark ignition systems on boilers or furnaces. So on something like this, we got 120 volts coming in, transformer, powers the blower over there. We got flame sensor and ground. The igniter. Usually, I'm trying to think. Yeah, I think pretty much all the ones I've seen, it's pretty common on spark ignition. Usually spark ignition, 1-year electrodes is the igniter electrode, and the other one is the flame sensor, also serves as the jumping point for the spark. Sometimes you will see spark ignition systems where you have just a separate ground rod, but generally it's 2, just because the flame sensor makes a good spot for the spark to go to. They got an air switch on here, run lamp, gas valve. I mean, it's all just standard stuff. As a matter of fact, this looks like they're basically picturing a standard Honeywell spark ignition module. So these are usually universal, basically. So there's nothing really fancy about infrared heaters, except for the way that they operate. They tend to heat the surfaces rather than the actual air, right? When it comes to combustion efficiency, we use the term AFUE, Annual Fuel Utilization Efficiency, and combustion efficiency are somewhat interchangeable. So how efficient the combustion is and the AFUE of a furnace should be pretty close to the same. But the AFUE of an appliance is determined in laboratory conditions. Obviously, the actual combustion efficiency is under real world conditions. So you're very rarely going to actually reach your AFUE in the field, but it should be very close. So I don't think we've discussed it in this class yet, but you can use heat rise methods to a heat rise method to determine how many CFM you're putting out. I think I talked to you guys about this before briefly too, but when you do it on a gas furnace, you need to know the BTUs you're outputting when you're doing something like that. Or if you need to know your BTU output in general, you need to know the AFUE of the furnace so that you can calculate what your actual output is. So if it's an 80,000 BTU furnace and your AFUE is 80%, then that 80,000 BTU furnace will put out actually 64,000 BTUs, right? But really, you're not even supposed to do that. You're supposed to clock your gas meter and determine how many BTUs you're actually putting out. That way you can actually determine, what's going on. But and use a combustion analyzer to determine the actual efficiency. But your numbers do end up so close enough that the margin of error is still there. So I guess the greater point is that you'll never really reach that AFUE, and you'll very rarely put out the exact BTUs that a piece of equipment says it will. But it's so close, you're within the standard margin of error of what things we do, so it's really not that important to get those exact numbers. So the reddish-brown haze often seen over urban areas is a combination of nitrogen dioxide and particles in the air. Most of the other nitrous oxides are colorless. So they're just talking about, smog basically. So you have air is 80% nitrogen, 20% oxygen. That's a little simplified. There is actually, a small sliver of other stuff in there. But for the most part, we're somewhere around 20% oxygen concentration in normal air. Fuel gas, once you reach combustion, you mix that fuel gas with the air while it's burning. You have 80% nitrogen and water vapor, 18.5% carbon dioxide, and 1.5% oxygen. And that is basically your dilution air, right? You're going to have a little bit more air than needed for complete combustion to make sure that you maintain complete combustion, because it's better to have a little too much air than a little bit less air than what you need. You don't want to have way too much air. But it's better to have a little bit more so that you make sure you've completely combusted all the fuel gas. Alright, both mechanical and electronic gas burner combustion test equipment generally come in kits that provide all the accessories needed. So yeah, when you get a combustion analyzer, usually it's going to come in a kit. And most of them these days are going to be electronic, and you're going to essentially follow the directions in the kit. I've used one a couple times. They give you really good instructions with equipment like this. Just like if you get equipment for measuring airflow and things like that, they generally come with very good instructions. So, when you get to, really all test equipment outside your multimeter and stuff, you should be reading the instructions that come in the kit, because a lot of them do a really good job about teaching you other things you should know. And they'll give you all the instructions you need to make sure you properly utilize it, and they'll give you information about what's good and what's not. A preliminary inspection before conducting a combustion analysis should include the following. You want to look for plugged or dirty supply air filters, rust or holes in vent connectors, holes in furnace heat exchangers, soot buildup that could indicate incomplete combustion, and restricted or blocked air intakes on all types of furnaces. So basically, you want to make sure that this test is going to be accurate and there's not any glaring problems that are going to mess up your results. Plugged or dirty supply air filters are going to increase the heat inside the combustion air chamber, or inside the combustion chamber, and you're going to end up with issues there. Rust or holes in vents connectors, obviously you may not be venting properly, or if you got a hole in the furnace heat exchanger, you're going to have an extra you're going to have more dilution air because that air is going to be pushing into the actual combustion chamber. Soot buildup. And if you see soot in equipment, pay very close attention to what's going on, because a lot of soot buildup is bad, and a lot of times it goes unnoticed for a long amount of time. But that is an indication that you have incomplete combustion, that you don't have enough air getting to the equipment, or something's burning improperly. It could be low gas pressure. Things like that can cause soot buildup as well. So you want to look for any of that. It can get extremely dangerous as well, so you always want to inspect any piece of equipment for signs that soot's building up on the inside, because that soot can catch fire as well and cause other issues, and it will block the air intake more, leading to more soot, which is why it tends to snowball into a huge issue. And then restricted or blocked air intakes, you need, again, enough air in the equipment. So a good example is those FVIR, the newer gas water heaters, often have screens at the bottom that can block the air intakes on them, and that will cause issues with combustion. If they stack too much stuff right in front of the combustion chamber, it can actually restrict the airflow going into the combustion chamber. If you have a 90% above furnace or something like that, then obviously the air intake going into the furnace can be blocked. So all of those things are important to look for. You should be checking that anytime you're working on a piece of gas equipment. All those. The other thing to look for is if there's combustion air openings in the room. So say the room is too small for the combustion equipment, or you get combustion air from the outside, or you get combustion air from other rooms in the space. You want to be checking to make sure that those aren't blocked off or anything, and that they're sized large enough. If you know how to size them, you can double check the sizing and make sure they were sized properly, because I've seen those undersized a lot of times, especially when people start adding equipment in rooms and things like that. So that's something else to look for. Here's some where you put your sample holes. So a natural draft furnace, you're going to put your sampling tube inside here, because most of the time with a natural draft furnace, this is where your flue gas comes out right up into the pipe right here. If you got a natural draft boiler, right above the vent connection is where you'll put your sample hole. 80% induced draft furnace, same location. 90% condensing furnace, same location basically. But your intake is going to go right there. Whereas with these, your intake is usually going to be the room itself. For flue gas temperature, to determine the actual flue gas temperature, you want measured stack temperature minus room temperature equals net stack temperature. So if the flue is 400 degrees, you subtract the temperature in the room, which, is probably going to be somewhere around 70 degrees most of the time, right? And you'll get a net stack temperature for 330 degrees. So that is what you're talking about when you're talking about net stack temperature. It's the difference of the flue gas compared to where it's getting its air. Okay, so if you had a room of 0 degrees, your flue temperature is going to be much lower, because you started with the lower temperature air to begin with for combustion. On condensing furnaces, substitute the temperature of the combustion air entering through the intake pipe for the room temperature. right? Because combustion on most condensing furnaces, you will get the air from outside. Not always. There are instances in which you can take combustion air from the room, in which case it would still be the same. It would be the room temperature. But if it's direct vent piped to the outside, then the air going through the intake is where you're going to get the entering air temperature for the flue. When readings do not agree precisely with the chart, you may have to extrapolate for improved accuracy. So this is telling you next temperature with your percentage of CO2 and your percentage of O2. This will be your combustion efficiency, right? So if your readings are in between, then you extrapolate the readings. So say the easiest example right here would be, say your net stack temperature wasn't 380 and it wasn't 400, but these were your concentrations of O2 and CO2, right? If it was 390, then 79.5 and 78.9, you're going to be somewhere in between there. So your actual AFUE, right, is probably going to be 79.7, right, because you're in between those two numbers. You can extrapolate that data. You can start to guess as to where you are. You know what I mean? And you don't really guess. You look at the difference between, the two spaces and the two spaces to figure it out. You should be able to get very close. But if you pay attention, if you had 5.7% O2 and 8.5% CO2 or something like that, and you were 370 degrees, then you would probably be somewhere between 80.3 and 79.5, and you could probably extrapolate that out to what would that be? Probably close to 79.9, something like that. You know what I mean? And if you can actually do a calculation to get it exact, but if you're talking about a couple percentage points where, like we are right here, it's not that important. But there are tables in which you need to be able to extrapolate data very well. Another good instance would be, like a charging chart. If your temperatures are outside of the range on a charging chart because it's really too cold outside or something like that, if you just take a couple readings, then you can probably extrapolate where you should be on that chart and whether or not it looks right. Things like that. So when you're dealing with fixed charts like this, you should be able to extrapolate data. I will say, though, that's why, if at all possible, I prefer equations over tables. So if it's possible to get an equation for what you're trying to figure out instead of a table, I would always err on the side of using the equation, because you can get much more accurate information if you're using math equations than you can going off of pre-made tables. But there's some things, like a lot of charging charts and things like that, where it's difficult to do that with a formula. There's very few things out there where you can get a formula for that, so you need to use a table. Some problems that can be found: high flue gas temperatures. Overfired burner with low airflow across the heat exchanger will give you a higher than normal flue gas temperature, which can be a problem. Low CO2 and oxygen levels, possible inadequate combustion air. High CO levels, incomplete combustion, lack of combustion air, or poor adjustments. Process in which so these are trade terms. A process in which exposure of a sensing rod to a flame produces a tiny current that can be sensed and used to control a gas valve. Flame rectification. I don't think we've used that term in the class yet. When we talked about flame sensors last class, we did not get into flame rectification, but that's what you call it. If the system has a flame sensor, then we are using flame rectification to prove combustion. Alright, a gas valve that precisely controls burner capacity by adjusting the flow to gas burners, or flow of gas to burners in small increments. A modulating gas valve. So that would be a gas valve, again, that just adjusts the flow of gas to the burners in steps at a time. So that's your more efficient equipment. Value needed to perform a combustion efficiency analysis calculated by subtracting the room temperature from the temperature measured in a furnace's vent or vent connector. We already talked about that. That is your net stack temperature. A wire screen used to cover ceramic grids in a gas-fired water heater that operates by a submerged flame is a reverberator. I'm not familiar with that, so you guys can learn more about that on your own. I wonder what that's in. A gas-fired heater operates by a submerged flame. I think I've seen boilers that work like that, possibly. Because I've seen boilers that have, I forget what they called them, but they have kind of like blankets that spread the flame out. They're, fireproof media, basically, that gives a much more even flame across the whole heat exchanger area. So I think I may have actually seen this before, but not recognized what it was. Method of gas-fired heater operation that uses burning gas within two-layer porous ceramic grids is a submerged flame. And then complete a combustion analysis, which, like I said, we probably won't do that. Alright, any questions on gas furnaces? Well, so far anyway. Before we go into the test, and you know what, I just realized I screwed up because I remember we were going to do the test at the beginning of a class so you guys would have easy access to it for review. So I'm sorry about that. You're going to have to skip through the video later if you need to look at it again to get to the test. But we'll go over the test in a minute. But since I've already done this, I want to just continue. So before we go on, I want to or before we go to the test, I want to talk about the sequence of operation on a furnace real quick. Since we're discussing it, I don't think we've actually gone over it, so let's go over it real quick, because that's usually going to be your easiest method of troubleshooting any issues on gas equipment. In my experience, the best way to approach troubleshooting any piece of gas equipment is just to understand the sequence and then identify where the sequence went wrong, because that will narrow it down very quickly when we're talking about gas equipment, because gas equipment always has a very, very specific sequence that it goes through, no matter what the gas equipment is, and it can change a little bit here and there, but for the most part it's very similar across gas equipment, and you will be able to recognize what went wrong in that process just by understanding the sequence. So this is something that obviously I'm going to give you a generic one. You will want to verify the sequence of operation for your particular piece of equipment if at all possible, but if you use a generic one, you will usually be very close to what we're doing. So let me get sequences of operation. And even if you're in commercial and residential are extremely similar when it comes to sequences of operation. Like I said, it tends to be the same across everything for the most part. Alright, camera's a little messed up here. Alright, let me Alright, so sequence of operation. This is for a hot surface igniter and an integrated furnace control. Alright, It's going to be very similar with a spark igniter. The only difference is when we say the igniter, um, when we say the igniter gets hot, what happens there instead, well, we'll talk about it when we get there. There's a couple small things that'll change. Maybe I'll try and write out those differences at some point. But the point is, for the most part, the sequence will be very, very similar. Preconditions for operation. You always want to make sure everything else is there before you try and troubleshoot a sequence of operation. Most of the time, the things the sequence of operation is not going to tell you is you got to have high voltage to your piece of equipment, a proper voltage of plus or minus 10% of the rated voltage for most furnaces or pieces of equipment. For most furnaces, actual gas furnaces, the polarity of the high voltage must also be correct. So if you've got neutral and hot mixed up on a gas furnace, it still will not work properly because you've got flame sensors and stuff that go to ground. They send signals to ground. So if the polarity is wrong, those signals won't go back to the board properly. And since they're mostly 120 volt, this is obviously primarily for 120 volt equipment, because 240 volt has no polarity, right? I mean, it does, but not in the sense we think about it generally. Anyhow, if you're talking about 120 volt gas equipment, the polarity does have to be correct. And usually you're going to find this problem on startup if someone has mixed up the hot and neutral on a circuit so the polarity is not correct. But if somebody's done any recent electrical work or something like that and the furnace just doesn't seem to be working right at all, it's not starting up, then it could be the polarity is wrong. In most circuit boards for furnaces, most integrated circuit boards are going to have a error code that tells you that the polarity is wrong, but some of them don't. So the only real way to know that might be an issue is to remember that polarity is actually important on a lot of gas furnaces. You have to have high voltage and fuses and breakers closed. That goes along with having proper voltage for the equipment. Power to low voltage control transformers, low voltage output at plus or minus 10% of rating. Low voltage and fuses and breakers closed. Any external power and control wires properly terminated and in good condition. If you've got some kind of issues with your wires, it's going to cause some problem that you may not be able to immediately figure out. So it's always good to double check. Does everything actually look like it's terminated properly? Are your connections tight? Is it in good condition? Are your wires causing the problem, or is the problem with the equipment itself? And then any external auxiliary safeties are in the closed position, like float switches, duct smoke detectors, etc. Alright, power sent from R to W on the thermostat. Power goes to the W terminal on the integrated furnace control. So your circuit board, the furnace control verifies the limit and rollout switch circuits are closed. So usually before it even tries to start up, it's going to already be sending 24 volts through your rollout switches and your limit switches. So if any of those are closed, it'll basically do nothing. So if you see that the furnace is doing nothing, it's usually one of a couple things. But if you've got 24 volts back to the board on W, or whatever your call for heat is, and absolutely nothing is happening, the first thing you do is check limit and rollout switches. And if you see any signs of flames that had gotten started to roll out or something like that, or any burning on any wires or anything like that, then that's the first thing you're probably checking anyway. But you always have 24 volts that travels through any flame or rollout switches to the furnace control and to the draft proving switch or pressure switch. Alright, then the integrated furnace control, or the circuit board, verifies the pressure switch circuit is open. So you'll usually have a pressure switch connected to your draft going out, your exhaust. If you got a 90%, you will probably have multiple pressure switches, one for intake, one for exhaust. High efficiency water heaters tend to have 3 switches. So you'll have one or multiple pressure switches that will need to be closed, but it always verifies first that the pressure switch circuit is open, because if the pressure switch is stuck closed but there's a problem, then if the equipment still fires, you'll have absolutely no vent, right? So the furnace always first verifies that the pressure switch was open, and then it watches it closed. So anytime a pressure switch is stuck closed, the furnace will not be able to fire. And that's the other thing that it can be if absolutely nothing happens. Then that's usually where it goes. Then the integrated furnace control energizes the inducer. So after those two things are verified, the inducer should come on. If the inducer does not come on, then there's no voltage to the inducer, so for some reason the switch that closes to the inducer is bad, or one of the other two things is wrong, right? After the pressure switch closes, the pre-purge cycle begins. So the inducer fan motor runs for 15 to 45 seconds to clear any residual gas from the burner. So that's in case it's short cycling or something. Before anything happens, it'll run the fan for 15 to 45 seconds just to verify that you're not starting with any gas already in the burners, because you don't want to have multiple tries for ignition and keep leaving a little bit of gas sitting in the burners, because then when it does light, you could end up with a little explosion, right? And we don't want little explosions. After the pressure, oh no, I just said that. Okay, after the completion of pre-purge, the hot surface igniter is energized for the igniter warm-up period. So after the inducer fan comes on, then the pressure switch closes, then the fan runs for a little bit, you'll get the igniter to warm up. So if it's a hot surface igniter, that's when you start to see it glow. So if you see the hot surface igniter glow, then you know that the inducer energized and the pressure switch closed. When the igniter warm-up period expires, the gas valve is energized and the trial for ignition begins. So 24 volts is sent to the main gas solenoid on the gas valve, generally generating an audible click. Gas travels through the burner manifold and the gas should ignite. Then ignition is proven via a flame sensor signal sent to the integrated furnace control. If the flame is not verified, gas will shut off after approximately 1 to 3 seconds. The main gas valve will close and the ignition process will begin after a predetermined amount of time, usually 30 to 90 seconds. If flame is not sensed after 3 ignition trials, the furnace will lock out. Fan on delay starts after 30 to 60 seconds. High voltage is sent to the blower motor. The other thing that may control the fan is an actual temperature switch to kick the fan on, but these days it's usually just a set time that it's delay on, just to let the blower get hot before the air starts to blow. And then the furnace runs until the thermostat is satisfied, power is removed from W, the main gas valve is de-energized, blower motor continues to run for 60 to 180 seconds. That's just to clear any residual heat from the heat exchanger, and then the blower motor is de-energized. Now, the only difference between this and intermittent spark ignition is going to be when you get with intermittent spark ignition, instead of the igniter warm-up period, it'll start sparking, and usually it's going to light a pilot first. Then the pilot will light, and that pilot will have to be sensed by the flame sensor. If the pilot flame is proven by the flame sensor, then the main gas will come on and the flames will come on. If the flame sensor does not sense the pilot light, then it'll cut back off and then go through that trial again. So the real big difference is that you'll see a spark instead of a glowing igniter, and the pilot is what gets proved by the flame sensor, not the main flame. It is possible that you'll have 2 flame sensors, one for the pilot, one for main gas, but that's pretty rare. Pilot lights are a very tried and true way to make sure that main gas comes on. They do a very good job because you've already got a fire right there. The fire will light the bigger fire, no problem. Whereas a hot surface igniter, even if it's glowing, sometimes will fail to light the gas off if it's not quite hot enough. So that is your sequence of operation. So once you understand that sequence, if you can, halfway memorize this, then every time you see something shut down, you can determine, what's going on. So if, a very common one would be the flame comes on, then goes off again after a few seconds. If the flame comes on and goes off again after a few seconds, then obviously you have something wrong with your flame sensor signal. Either the board's not getting it properly or the flame sensor's not sending it properly. Usually because of a dirty flame sensor, but also possibly because of a faulty control or bad ground. But you know that as soon as you see that flame come on for a few seconds, pretty much everything's working, but there's an issue with the flame rectification system, right? If it seems like everything's going, but you never see the hot surface igniter warm up, then either the pressure switch isn't closing or power's not getting sent to the hot surface igniter for some reason. So, you can basically look at any step in this sequence and determine what one or two components you're generally looking at to find the problem. And that's, once you get used to it, it's a very quick way to determine what's going on with a furnace ignition system. All right, 9 times out of 10, you don't need any tools to figure out what the hell is going wrong with the sequence. You might need a meter, you might need a screwdriver, but other than that, a gas system is pretty easy to determine what the issue is just by looking at where it gets caught up in the sequence. Obviously, the most likely things to fail are the the flame sensor getting dirty, the hot surface igniter going bad, and the pressure switch sticking, because those pressure switches like to stick. And then obviously an inducer motor could fail. So that is your sequence of operation for a furnace. And then if you guys look, when I sent you that link for the handouts and stuff, you've got a schematic here that you can look over that will give you an idea of how it's usually hooked up to a board. As a matter of fact, I really need to do one of these with the universal control, but you have a picture. If you look at, like I said, the infrared heater one, that's a good universal picture of a universal, like Honeywell style furnace control or something, hot surface ignition control. But this is, assuming a circuit board where you have relays and you've got connections here, usually a fuse, and then you'll have a limit switch, a rollout switch, a draft proving switch or a pressure switch, gas valve, flame sensor. So it kind of gives you an idea of what's going on there and where the power goes through the circuit and what happens. All right. With that being said, let's go ahead and start going over the test. I need to stop sharing this screen. I need to switch to something else. Should be easy test. Alright, give me just a second, guys. God dang it. Alright, I'll be right back. What is your problem? Why are they Alright, sorry about that. Alright, so, any questions so far on any of that stuff, guys, before we get to something else? Are you all good? How good are you guys with gas equipment? A lot of you guys work on gas equipment. I know a lot of you guys are commercial. Everybody go take a nap. It's not bad. Like I said, sequence of operation is the most important thing. So if you ever have to troubleshoot one, just try and look at the sequence. Well, most of them these days have flashing lights that tell you what goes wrong anyway. And that'll usually point you in the right direction. Basically, that light just flashes based on where the sequence messed up, and that tells you where to look. Bunch of rooftop units. Yeah, rooftop units. Again, rooftop units pretty much the same sequence as even residential. It's really simple. Okay. So the test. Questions on your test. So first one, you want to make sure you understand what happens in that sequence, right? You want to make sure you understand the sequence of operation. So what happens when the pilot flame is proven on a furnace that uses spark ignition to light the pilot? I talked about that briefly, but once you know that the pilot is lit, the next thing that's going to happen is the burner should light right up. The gas valve should open and the burner should light up. If that does not happen, then you will want to oh, okay, I guess this is alright, so that would be my answer, and my answer would be wrong on your test. So to give you guys a heads up, I guess, the next thing that happens once the flame is proven on a spark ignition system is actually the sparking stops. Okay, so remember that. The sparking stops as soon as that flame is sensed, and then your burner's light. I don't really think about that as a step in the sequence, but that is an indication that something's going wrong in the sequence. If the spark igniter continues to spark, if it continues to spark even after the pilot is lit, then you know that it's not sensing the flame as well, right? Even though the whole ignition sequence will stop at some point when that happens. The spark igniter continuing to spark is an indication that it is not sensing the flame. Alright, again, the next question is all about understanding the sequence. So it's going to ask you things that are not part of a sequence on a natural draft furnace. Remember, natural draft furnaces are natural draft, so they're not going to have inducers and things like that to help with the draft. An inducer comes on to assist. It's a draft assistance device, right? It's there to try and maintain a draft, especially at the beginning of operation, because like when a natural draft, your best example of natural draft equipment these days is your regular water heaters, right? Natural draft equipment tends to be somewhere in the range of 60% efficient. And when a natural draft appliance first starts up, it's not drafting because the flue has to get hot. The draft is caused by the stack effect, which is the cooler air tends to drop and more warm buoyant air tends to rise. Okay, heat doesn't rise, but warm air does rise. So the warmer the air, the more it rises. So you create a stack effect as the flue gets hot. The entire flue begins to get hot, and all the air tends to travel up and through the flue. So if once it first start when it first starts up, it's not hot enough to cause that stack effect, so you will get some spillage of combustion products into the room for a short period of time, but that should cease very quickly. So that's something to keep in mind. the old trick of using a lighter to test the draft, where you put the lighter real close to the draft hood and see that it gets sucked up into the flue, is not going to work when it first starts up. You got to let that flue get warm for a couple minutes, and then you should be getting a good draft up the flue. But on those natural draft appliances, you won't have inducers and pressure switches and things like that to prove the draft. So you need to prove that draft manually, semi-regularly, to make sure that everything's working right, because there's a lot less safety devices to help you in case there's a failure on that equipment drafting. So just understand the components that are not a part of natural draft equipment, as opposed to induced draft equipment or 90% direct vent equipment. We talked about thermocouples under load. So you want to either know in your book where to look for, or understand what the voltage of a thermocouple under load should be. We talked about that last class, but make sure you know what your reading should be on a thermocouple that you're testing with it disconnected, as opposed to if you're connecting it under load. That is in your book, so make sure you know where that's at. Understand what the components used to test to sense your flame coming on. So if you have a natural draft appliance with a pilot, you're usually going to prove flame if it's got a standing pilot. A standing pilot means the pilot is lit all the time. Any piece of equipment with a standing pilot is usually going to prove flame via a thermocouple. Again, a pilot sitting there, a lit flame sitting there next to the burner, is a surefire way to make sure that if that main gas comes on, it's going to light. It's just not going to fail ignition if you've got a standing pilot there. So you prove that the pilot stays on with the thermocouple, and that allows main gas to come on when necessary to prove that main gas is on. If you have intermittent spark ignition or a hot surface igniter, is generally going to be done with a flame rod. I guess you could, if you set up a long enough sequence, you could probably prove intermittent spark ignition with a thermocouple, but I've never seen it done. It's always been with a flame sensor, because a flame sensor is a way to quickly sense that the flame is there. So a flame sensor is slightly more likely to fail than a thermocouple. So even if everything's lighting properly, a flame sensor may not sense the flame, but it acts a lot quicker than a thermocouple, because a thermocouple takes generally 10 to 30 seconds to get warm enough to create a large enough voltage that you will sense the flame. Okay, so thermocouples are on natural draft equipment, basically standing pilot systems, and flame sensors are on more efficient equipment, intermittent spark ignition and hot surface ignition. Let me make sure I get the right answer on this and I'm not missing something. I'm sure I'm not, but just in case. Yep. All right, so one thing to remember is on gas equipment, grounds are very important. So if you have a bad ground, I don't know if you guys have ever had a vehicle with a bad ground, but a vehicle with a bad ground can start to act really funny, right? The computer doesn't work right. And that's for slightly different reasons than a furnace, but it's the same principle. You have to have good grounds on most equipment with circuit boards. Okay, but it's even more important on a furnace than something else, and that is the primary reason for that. If you guys remember right, when I was talking about polarity, is bad grounds and improper polarity can cause your flame sensor not to sense the flame. So if you've got an issue where the flame sensor doesn't seem to be working properly, Then your next steps are: one, verify all the grounds look good on the equipment. You've got good clean ground connections and they appear to be in good condition. The wire appears to be in good condition and all that. So if the flame sensor seems clean, the ceramic doesn't look like it's cracked on a flame sensor, then you check the ground and make sure that looks good, and then you actually measure the current through the flame sensor in microamps and make sure it's right for that piece of equipment. A lot of equipment can work at a lower flame sensing reading, whatever you want to call it, a lower current than what's labeled on the equipment, but I want to say what? I'd have to go back to the other PowerPoint. I think it's 5 microamps. I always got to double check it too. I want to say it's right around 5 microamps is usually the lower limit on that current reading. But and 10 is about normal. But you want to make sure that you're getting something in that range. You're not getting something real low like 1 or 2 microamps or something like that. But that would be your next step. If all that checks out, then usually it's a faulty circuit board. But you want to make sure before you go condemning the circuit board that you have checked the condition of the flame sensor and cleaned it. You want to make sure that you've checked all the grounds and make sure the grounds are good. And then you want to actually check the signal that you're getting from the flame sensor to see if it's adequate. But if you're testing the signal through the flame sensor, you could get a good reading even though the board's not getting a good reading because it has a faulty ground. If a gas furnace consistently cycles off on the temperature limit switch, a likely cause is... I just read that question out for you, so hopefully all you guys get this one right. What did it say? Yeah. I'm just making sure that I give you guys the right information. There's not a weird answer or something. Alright. So, if you're getting a furnace that cycles on and off because it's getting too hot, the temperature limit switch is there in case the temperature gets too hot. And this goes for anything, not just a gas furnace. Electric heaters usually have some kind of temperature limit switch. Pretty much anything that produces heat is going to have some kind of limit switch. The issue is usually something to do with airflow, right? You could have a dirty air filter. You could have a dirty blower wheel. You could have too many vents closed, too many dampers closed, anything like that. You're looking for issues that will restrict airflow because that means the air is moving too slow across the heat exchanger and the temperature is rising too much. So that is what you're looking for on a piece of equipment that cycles off on the limit switch a lot. I see this a lot in VAVs, actually. VAVs with electric heaters in commercial buildings. For whatever reason, sometimes the fan is not powerful enough on its own to handle the heater kit that was installed. The heater kit is oversized for the airflow that blower can put out. So you will often have to adjust them. You'll have to adjust the primary air damper in the VAV from the rooftop unit to provide some extra airflow to keep the electric heaters from cycling on and off, especially the second stage. So if you see a VAV that's cycling on and off, stage 1 stays on, but stage 2 goes on for a minute or so and then shuts off, and on for a minute or so and shuts off, and it continues to do that, it's cycling on a limit switch for that stage. And or first stage will come on. If it's got a single limit switch, first stage will come on. It'll run for a bit, then second stage will come on, and then it'll cycle on the limit switch, and then it'll repeat. Then you may have to give that thing more air, but obviously first you check that the blower inside of the VAV is working properly and it doesn't have a dirty air filter and yada yada. But that is what you're looking for in something that cycles on and off, is some kind of airflow issue. The other thing to keep in mind, especially with condos, if you ever work in condos or commercial buildings where it penetrates a firewall, there'll be fire dampers a lot of times off of the furnace, and if the furnace is overheating, it can get those fire dampers to close. So you'll think you found the issue when you open up the fire damper, but then you find the issue later on that caused the fire damper to close, because that fire damper will close at 160 or 180 degrees most of the time, and that is pretty close to a supply air temperature from a furnace. Supply air temperature from a furnace, 140 isn't outside of the realm of reason sometimes, 130, 140. So it only takes a small amount of airflow drop at that point to be enough to trigger the fire damper, the fusible link in a fire damper. So remember too, pro tip, because I don't think we really discuss I don't know if we get a chance to go over any code in this class, but pro tip is that a fusible link in a fire damper is allowed to be set at 50 degrees higher than the normal temperature in the system. And the normal temperature in a furnace is usually, going to be about 130. So you will want the fire damper fusible link to be at least 180, and that'll make it a little less likely that you'll get the nuisance trip from a fire damper than if you get one that's set for 160 or something. But anyway, if you see a fire damper closed off of a furnace, don't assume that's what's causing the furnace to cycle off a limit, because there's probably something else that was causing a problem before that. An inducer in a condensing furnace. This is another question about the sequence of operation, basically. So, I mean, again, make sure you understand that sequence. What can I tell you guys about this without just giving away the whole question? Yeah, I don't know. Understand your sequence of operation. If you have an issue, again, once that inducer starts running, what's going to happen after the inducer runs? It's got to close a pressure switch, right? If the pressure switch doesn't close, then you've got some issue with the draft. If you've got some issue with the draft, what could it be? When you're talking about a condensing furnace, the problem could be on the intake or the exhaust. So, what could that problem be that would cause the burners not to light even though your inducer is on? Well, you're not closing the pressure switch for some reason. What's keeping you from closing the pressure switch? Usually some kind of blockage or something of that nature. Now we get into infrared heaters, which is not my strong suit. I've only worked on a handful. But, as I told you, infrared heaters are extremely similar to furnaces. So just remember that. Infrared heaters are extremely similar to gas furnaces, so the safety devices and controls are going to be relatively the same, and that's how they operate. So that's what you need to remember. Remember what a reverberator is. A reverberator. Again, I've got no experience to give you guys concerning that. I can't tell you anything particularly about them, but remember we said it's kind of like a screen, right? It looks kind of like a screen. That's a reverberator and a piece of gas equipment. Hmm. Oh. Um. anytime you have non-vented equipment, just remember this. There are some small equipments. A lot of times it'll be listed as a decorative appliance, right? That's your most common non-vented equipment, is something that gets labeled a decorative appliance. So it's a very low output fireplace or something like that. Um, or small room heaters sometimes are non-vented. Usually if it's under a certain number of BTUs, it might get approved to be non-vented. But you can have non-vented infrared heaters, right? If you have a non-vented infrared heater, um, or any other non-vented appliance, you want to make sure that that thing is an area that is well ventilated, right? You don't put a non-vented appliance in a very non-vented room, so you're not going to stick a non-vented heater in a small bathroom or something, right? Because there's not enough ventilation in the room to deal with the product's combustion. Because just because it's labeled to not require a vent doesn't mean that it's not going to have products of combustion that need to be vented. They will be in such low levels that it's most likely safe in most instances, but those need to go in well ventilated areas. So typically, especially with infrared heaters, you're going to see those non-vented types in things like repair garages and things like that. Something that's already well ventilated, that you have large doors open a lot of the time, so that the venting isn't a concern, really. That's something just to keep in mind. Thermostats. There's certain thermostats you're not going to want to use with an infrared heater because it's not going to do a good job of sensing or of turning it on and off. And a typical room thermostat isn't going to be something you're going to want to use with an infrared heater, because the infrared heater heats surfaces, so it'll heat that room thermostat before the room gets heated. So read through your book on what thermostats tend to be better with infrared heaters. Most of the time that I've worked on them, it's been in repair garages and things like that. So they're usually just on switches or thermostats that are placed well out of the way of the heater. But your book should give you some options on things that are more recommended, I guess. But typical room thermostats aren't what you'll want to be using with them. Know how to calculate net stack temperature? Remember how to calculate it. Remember, it's going to be your actual stack temperature that you read with the thermometer minus the room temperature. And that's going to give you an idea of how much heat is being created by combustion. So remember net stack temperature and what it identifies. And know how to calculate it. You got a question on where you have a question on your test where you'll have to be able to calculate it, so make sure you know how to do it. I've just said it. We've said it multiple times in the class, but you'll need to remember that because you'll have to do an equation on it. I'm just checking. What? Yeah. Yeah. Remember, I guess I'll just tell you. Remember, high temperature rise in a furnace is going to create higher flue gas temperatures, right? The high temperature rise across the furnace heat exchanger is not an issue with combustion necessarily, right? It's not going to necessarily cause many issues on the combustion side of things, but it causes other problems that that can lead to you having an issue there eventually. But generally, the reason we want a low temperature rise is to protect a lower temperature rise is to protect the integrity of the heat exchanger and the components of the flue. It's not necessarily because we're going to have carbon monoxide or condensation or anything like that. Now, too low a flue gas temperature can cause condensation, but higher flue temperatures aren't necessarily the worst thing in the world. Especially on natural draft equipment, it's going to be relatively normal to have a high temperature rise, but you could end up with damage to your heat exchanger or something like that. And yeah, excessive draft through a flue vent. Excessive draft through a flue vent can cause poor combustion efficiency. Just remember that. And that is the extent of your all's test when you have to go through it. So if you remember everything I just told you, or know where to find those answers in your book, you should be good. Shouldn't have any issues. So we've covered that in the last test. We will find out when we take that. Then on next week, we will start the next module. The next module is on, let's look, see what we're doing. That was 5, so this should be 6. What are we doing next? I think we're doing oil, right? Yep. The next module is oil, and I've said it once and I'll say it again. Oil's not my thing. Haven't worked on a lot of it. Can't give you guys any stories. We will describe how it operates and describe the differences between that and standard gas equipment, but oil is its own animal, and there's not that much of it around here, and a lot of times your oil companies handle it, so I don't get much practice with oil. But again, I will tell you, if you're working on oil, you should definitely know how to use a combustion analyzer then, because it's extremely important with oil, because there's a lot more field adjustments that you make with oil than with other equipment. So it's extremely important to be able to properly adjust an oil burning piece of equipment, whether it be a boiler or a furnace. So we'll go over that briefly, but we're going to cover that in one quick class and talk about the test, and then we will get into troubleshooting accessories, which should be relatively quick as well, I guess. So 2 more easy classes and another test, and we'll go from there. Alright guys, any questions, concerns, criticisms, complaints? Did I not cover gas stuff enough for you? Is there anything else you wanted to know about gas equipment in general?
Don't forget to upload the videos.
Yep, I will. I gotta pre-record a video tonight as well, so I will. As a matter of fact, let me stop recording.